Sorry, I forgot to hit record. So, what is the difference between like what an acid does in a reaction and what a base does in a reaction?
Like the acid donates hydrogen.
Yeah, or it
Or
accepts electrons, right? Versus a
yeah,
base does what?
donates the electrons.
Yeah,
Or
yeah,
yeah,
yeah. It uses its own electrons to interact with whatever the
yeah, to
acid
like
is, right?
pick
But
up the hydrogen.
yeah,
Yeah.
yeah, pick up a hydrogen if it's right, or to in the case of a Lewis base to interact with another atom to
Yeah, or
create
to
some
just
sort
like
of
act as a nucleophile to like attach.
exactly.
Yeah.
Yeah,
Okay.
exactly, to create a bond. So in this case, let's look at this. Whoops. Let's look at this, right? This is our base. And I'm just gonna do this real quick to like get rid of this so we can just see it for what it is, right? So this over here is our base, okay? Now, where else could this base? So what you're asking is, you find that the base is reacting with the central carbon that I just put in orange. Whereas an acid is going to protonate, say, this oxygen, just in this example, right? So you're asking, why does the base react with the central carbon as opposed to where else would you suggest that the base react to?
I guess the only other like possible function it could have, which isn't really helpful, but like it could, it's like technically on the carbon there's like methyls. So it could like steal protons from there.
So what
Like,
you're saying is there's these here.
yeah. So like theoretically it could like take a like because like my thing is just that like the carbon is already like saturated. So I get that like you could do curved arrow pushing. I just didn't know why it would like automatically go and attack the carbon.
Well, because
Because
so
like isn't
when
that like stable? Like isn't it already stable like an acetyl? Like it doesn't need
do
it, right?
you remember this?
Yeah.
We have this kind of like little dipole. Is
Yeah.
there any dipole on this methyl?
No. Well, no, not really.
No. Like we consider carbon and hydrogen to have the same electronegativity, so there's no dipole. So there's
Oh,
nowhere for this to react to. Because this also has, well, first of all, it's not even a dipole, it's like a formal negative charge. But let's just say it even was a dipole and we had another hydrogen on there, right? This wouldn't make it a base anymore, but you get what I'm saying. Let's just say
yeah,
even
I
if it
see
was.
it.
But
Yeah.
see how like there's nowhere like this can't react with the methyl because this is a neutral, this is neutral.
Yeah, I see now.
Whereas this over here, this central carbon has that partial positive charge due to, and especially this carbon, because we have two oxygens that are pulling the electrons away from it. So that's why we would have that reaction in on that central carbon.
Mm. Okay.
That makes sense?
Yeah, no, it makes sense.
Cool.
Also, can you go over what like the defining characteristic is of a hydrate? Because that was brought up earlier. It was, let me find it. Um, and I just didn't know how to like, because normally I thought the way you know it's a hydrate is literally if it's like the dot and then it says H2O. But from the line angle drawing, I didn't know how you identify something as a hydrate.
Do you have, so a hydrate is like something that has water or like, or has some, constituent of those elements in it so that
Yeah,
you can
I
get water?
I
Do you
found
have a
it. It's
specific example?
on,
Yeah.
yeah, it's on page 4.
Of aldehydes?
Yeah.
Let me just
Like, and like, because I
3.4.
this one, yeah, it has one alcohol and one hydrogen, but then um I looked it up and I was like, does any molecule that has an alcohol and a hydrogen make it a hydrate? And it said no.
Okay, so this is roughly where 4 is. Addition of water. Okay,
You
this is this stuff.
go to the part literally where it's like section 3.4 hydrate formation.
Yeah, I don't have that on here. I think I only have
Oh,
it. But that's okay. I can read it because I have my book with me. I just wanted to see if I had it. Okay, so recall addition of water across the carbon-carbon bond is exothermic and generally not
oh wait,
reversible.
it's the example right before the one that is on the top of your screen right now.
Okay, so we have already seen that the ketone, no, okay, that's this. Okay, so compare acid base catalyzed addition of water to carbon oxygen bond. However, it's not exothermic and is often reversible at room temperature. Is that what we're talking about?
And then it says that that product is a hydrate.
Yeah, so the reason for this is that, yeah, it's a hydrate because you're adding water to that, which makes it like you could dehydrate it, right? Like if you hydrate a molecule, you're adding water, typically an alcohol and a hydrogen across the double bond in some way. You're adding water to that molecule. What was it that you said you looked up that said that that's not that? What was it that you said? Sorry, I just want to make
So
sure I
I
understand.
just looked up if like a molecule has the alcohol and the hydrogen on it, as is like the case in this example, like does that make it a hydrate? And it said no.
Yeah, just because there are alcohols or hydrogens on a molecule doesn't necessarily make it a hydrate. But if it's something where there's that where you can create, because you can't always, like, for example, it says like in the example directly above it, when we're adding water across the carbon-carbon bond, that wouldn't be a hydrate because you can't get it back, right? Like you can't get the water back, it's irreversible. So like it's a hydrolysis reaction, but it's not, but like you can only, like it would be considered a hydrate if you could get a water out of it. Does that make sense?
Yeah, no, I see the distinction. But in the first one, on the point of irreversibility,
Yeah.
you figure that out based on the comparison of enthalpy and entropy, right?
Yeah, basically what they're saying is that excuse me, a pi bond and a sigma bond versus two sigma bonds, you have more stability um, with the two sigma bonds, and you're going from two molecules to one.
Mhm.
So both decrease, right? Your enthalpy and your entropy decrease, but in the second one, um, the enthalpy, yeah. So, but in the second one, you have it's not exothermic. Wait, why was this? Because this one also goes 2 to 1 as well. I just don't want to say this wrong. So you're also getting the pi, the pi and the sigma to two sigmas. But there
Oh,
was
I
something.
know. I see it. It's because the first one is the carbon-carbon bond, and then that one is weaker than a carbon
Oh yeah,
oxygen.
yeah. The pi. Yeah, that's what it is. The pi bond of between a carbon and an oxygen is stronger than what would be between a carbon and a carbon because of that electronegativity.
Yeah.
Because
So like
carbon
it
is
would,
not, yeah, and carbon isn't as electronegative as oxygen.
okay.
Yeah.
Okay, yeah. Okay.
So it's actually just a stronger pi bond. And so that pi bond has more like stability, more kind of strength over the two sigma bonds, like the entropy, the enthalpy decreases more with having that sigma pi carbon oxygen, as opposed to the entropy that decreases from going from 2 to 1 molecule. Does that make sense?
Mm-hmm.
Like if you looked at them on a relative scale.
Mm-hmm. Yeah, no, I see that now. Also, on another note, but kind of going back to the thing we talked about first, if you go
Yes.
back to page 8,
Back to page 8, so scroll this way. Oh, I'm
for
already here.
oh, it's like hydrolysis reactions. It's 3.7.
Yes, it's
Go down a little further.
Oh, it's down. Okay. Oh, right
Yeah,
here. Yeah,
right.
here we go.
Yeah, right there. Yeah, so I was just wondering if you could explain how you know where to
Cut the
break
bonds.
the bonds. Like, why is it that it's always next to the carbon?
So again, this is so for this we have, again, this is kind of that we've seen this already, right? Where like this is kind of like our placeholder. Like that's how we got to this, correct? Like these being the placeholder to like keep reactions from happening.
Oh, like the protecting group?
Yeah, the protecting group, yeah.
Yeah.
Placeholder, protecting, all the
Yeah.
same. Yeah, so your protecting group. But does that must come later in this section though, because I know it's
I don't recall what the order. Oh yeah, the order. Yeah, I just scrolled down. It's 3.8 introduction.
Oh, okay, it's literally that next one. Okay, yeah. So anyway, regardless, it would break there as opposed to I want to understand like what your train of thought is like where else would it or could it break? So like the reason why we're breaking it here is we're attacking this what's going on? Oh, we're attacking that carbon in particular, right? We're adding whatever it is to that carbon. So I guess in this one we're protonating. Sorry, we're not doing base. This is acid. So yeah. So
like I
yeah.
see what you're saying. I just more like I guess my question more is like
This is a good leaving group. Remember, these are good leaving groups. They're stable.
so like so like the acetyl. I guess what I'm trying to get at is um like why would you think that the acetyl would like want to break? Is it because of the dipole thing again? Or
So
like why would you like thought go to okay, like we want to break these bonds here to like because we're in the presence of water. Like I guess that's why.
well, yeah, again, because it's a good leaving, like these are good leaving groups, right? So we're protonating. And I think you're gonna come up on it. Maybe it's in the next section where it's like plus H minus H plus H minus H, and you do like 15-step reactions, and it's literally just protonating and deprotonating in different.
Yeah, that was further in the section.
Oh, it is in this section. Okay, yeah. Those are fun. But anyway, yeah, so it literally is just because it becomes a good leaving group, right? Like oxygen, because again, when you protonate this, think about this is like there's a lot of these going on, right? We have a high concentration of acid, so that's what's going to push it in that direction to get water, because our content, a lot of this stuff also has to do with like concentrations, right? So like if we have a lot of acid and then we have these kind of like rando oxygens on here, whatever, like they're gonna pick up the hydrogen. That's kind of what they do. They love to make bonds with hydrogens because then they become this over here because they're more stable. They become a good leaving group, right? So that's what pushes. So the high concentration of our acid is what pushes things in this direction to give us these leaving groups here. Now, if we had like no acid or like a drop of acid, it probably wouldn't, right? So a lot of it also has to do with your environment. But like in these, when we see this means acid workup step. Like that's literally what that means. So that means that we're dumping, not literally, figuratively, right? But like dumping acid in there to get these reactions to happen.
Yeah, I
Same
just
thing
have a
with,
question. I just,
yeah,
sorry. I
no,
just
no,
have a question though, still on the first one. So
yeah,
when those bonds break, we now have, like, I'm trying to just like count electrons because I guess this is also where I'm confused.
yeah.
When you break the bond, you have two more electrons available, if you will, for each of the OR groups. And then,
Wait, because
right?
what we're doing is we're taking,
And then you use that to bond to the hydrogen.
yeah, so
But then,
no,
but
not really.
no.
Like, so what happens is you do this first. You do this first. And then you have,
Okay, yeah.
right?
And then you okay,
And
then you
then
put the
this,
electrons on the oxygen.
yeah.
But okay, yeah. And I okay, so but regardless, the electrons are no longer on the carbon. So then
Yeah.
where do you get the four electrons to make the double bond with the oxygen?
So then, yeah, so basically you're asking like what the mechanism is, right? Like, so this leaves, and then you have, so let's see, this, let me see. We have our H and we have O and we have R prime. Oh, I guess this is for this one, but yeah, okay. And then we have, so this one has broken up, and so now what we have is this right here. C O R, because I keep thinking about these, and so that's why I keep pausing, because I'm like, wait, I'm not doing that. Okay, so R prime, this could actually be like double prime if it was something else, but anyway, that's neither here nor there. So then we have this here, right? And we have this, I don't know why it keeps doing that. Okay, we have this positive charge here, let's just say, right? And then we have H and we have R, right? And then so we have this strong at, like, we have more H3Os.
You do the same thing as the other side, right?
Yeah. So then you have one of these that attaches here. No, wait, sorry. You would have this water, not that. You'd have water that would attach there. So then water, because remember, we're also in the presence of water, so water would come and attach here. So then what we would have is we would have C O H O R prime H R, and then you would say you would have H3O, right? That would
Wait,
come
what
and
about the other hydrogen?
protonate this. Which other hydrogen?
You know, you're attaching water to the carbon, so why is it
Oh,
just
sorry. Yeah, sorry. What would happen is another water would come and pick that up. Sorry.
oh and deprotonate it?
Yeah, exactly. And then these would go here. Yeah,
Oh,
yeah.
okay.
And then this one would come and knock off, and then you would have a positive here, right? And then another water would come and protonate this, because remember our acid is, and another water would come and protonate this, and these would go here. And so that's how you would have it. So the oxygen, this oxygen did not come from either of these. That's an important thing to know. This oxygen here is completely different. It came from your solution.
Yeah, so just one more question though. For the OR group that's on the right,
Yep.
I thought that like do you see on the last molecule you drew like the OR group is still attached to the carbon?
This one down here. Whoops.
Yeah.
Yeah, this one down here. Yeah.
Yeah. So that doesn't leave in the beginning when when it's equal on the other
Well,
side
okay.
leaves.
I'm going to give you the same spiel I've given you a couple times. Remember, all this stuff is happening a million times and it's going on like at speeds beyond our comprehension, and everything is kind of rearranging and doing this and doing that. So for the sake of writing it down as a almost mathematical step-by-step process, I don't have the capabilities of showing that, right? But that's why, like, we have to kind of think about these mechanism problems as in, like, okay, this would happen, then this would happen, then this would happen. Now, if what you're saying is, oh, well, wouldn't both of these leave at the same time? No, because then we would have two positive charges on a carbon. Like, that definitely wouldn't happen, right? So you're going to have one that's going to break off, and then it's going, and then at almost simultaneously, not literally, but pretty close, and this other oxygen, this water molecule is going to come and hop on there. And then around that same millisecond of time, this other acid is going to deprotonate on this side now, because now this carbon's stable because it has another oxygen, like oxygen and hydrogen on it, right? That'll get deprotonated as well. But we have another oxygen on there so that we're able to add another positive charge on there. And so then we have that other positive charge. Now this oxygen over here is like, well, bye hydrogen, see you later. I'm gonna steal your electron so I can make this stronger pi bond with this carbon, as opposed to my like weak little sigma bond with you.
Yeah. Yeah, I
Right?
see. Yeah, and just one more thing. So with
Yeah.
water, I know water can act as like an acid or a base, but just based on like,
Depending on the environment.
yeah, but just based on like the patterns that I feel like are like present in like these examples, would you say it's like correct to say like most commonly like the water like in this case is like acting as like a nucleophile to either attack the central carbon, or its function is like deprotonation to basically like assume the hydrogen to make hydronium? Are those its two like use cases?
That would be in this, yes. Yes, it is attacking the central carbon, the only carbon. Well, no, the only carbon of ours. It is attacking the central carbon, and it is protonating or deprotonating. It is deprotonating the OH that
Yeah, so like
it's
basically,
adding, yeah, it's at one with like this is where it gets confusing, right? One molecule is going to be added to the central carbon, and then another water molecule is going to come and deprotonate that.
yeah, so like, so I think maybe a reason why I struggle with the mechanisms is I'm not sure exactly like when it's appropriate to do like the protonations, deprotonations. So like, how do you decide, like even just like, for this example, like how do you know that water is going to come in, attack carbon, and then it's going to get deprotonated? Like, can you just maybe like explain like how you come to like know that?
Well, practice, right? As they call it in this class, heuristics, right? But in this case, we are given two. I'm just gonna erase my work. Okay. In this case, we're given a starting point and an ending point, right? Like if somebody just said, without me knowing anything, right? And if somebody just, whoops, boy, okay, sorry. Now, without me knowing anything, and somebody just said to me, like, hey, I'm going to give you this molecule. I'm not going to tell you what it is or anything. And then we're going to put it in the solution as an undergraduate in your first time ever seeing this stuff. What does it make? I would be like, I don't know, right? Luckily, in this example, right, we have both our beginning, our reactant, and our products, our end, right? And we're given that this is the environment in which makes this happen, right? And we know that it's going in this direction because of the arrow, right? Now, based on, because this knowledge is going to build, right? And that's why, like in this case, we are working on this so that we can see how this is very similar to how this happens here, which we will use later on for mechanisms. So right now, in this example, you're learning patterns. You are just associating these patterns, and it's not necessarily that like it is intuitive, by any means, but it is through practice, sheer practice, that you are starting to associate these patterns of seeing, okay, when I have something like this, my acetyl, for example, and I am trying to make this ketone where I have these two side products like this, how would that happen? Well, based on what I know, this has to be protonated in order to become a good leaving group. Nothing is going to leave because nothing is a good leaving group as it is. Now, if we saw bromine on there, we would say, okay, cool, that one can just leave on its own because it's happy to be an anion with all those electrons on it, right? But we don't see that. So we see that we have like a fairly happy molecule. So we say, okay, well, because this is an acidic solution, I know that, which means that I have a higher concentration of acid, aka a lot of protons hanging out, right? Because remember that acid, all that is this, right? It's water with some extra protons. So they get to like fly around and go around and do whatever they want. Well, if I need to make this molecule here, then that means that this needs to be a good leaving group. The only way to make that a good leaving group is to protonate it. Then once I protonate it, then I know that it will happily leave and become this, and that gives me something else to work with. Well, when that happens, that means that this is going to have a positive charge, right? Well, in my solution, I have water. Obviously, this is not going to hop on there because it's already positive. Oxygen doesn't like to be positive, but water will hop on there. Water's happy to do that. So water hops on, right? And adds this OH, whatever. And then so now now that's a positive, right? So now we have this pot because we already have two, plus we have this new bond with the carbon. So now we know that it needs to be deprotonated to become happy. So another oxygen or another water molecule comes along, and like any good catalyst, everything is regenerated, right? Another water molecule comes along and steals one of those hydrogen because it's happier to have that bond. Oxygen, as we know, is going to have a stronger bond with carbon than it will with hydrogen, right? And so it just becomes that kind of pattern of mechanistic workings that we start to see what these patterns look like. And then we can kind of decipher step by step. Now, I would say this all knowing full well that when it comes to exam time and you have 50 minutes or an hour and 20 minutes, however long you have, and you're given a bunch of equations and you're like in panic mode a little bit, because who doesn't have a little bit of test anxiety, right? It can be really difficult to remember some of these like kind of basic principle rules that we created back in OChem 1, right? So that's why practicing this stuff, practicing these mechanisms, and just remembering what some of these like original rules are is really helpful in learning how to incorporate that into when we start getting to these like what the heck is this thing? I've never seen that before, right? And so we still get to rely on those original principles. Does that make sense?
Yeah. No, I see. Also, like, let me just find, I just have to scroll down and find,
Yeah, no worries. And also, I will say, as you've probably seen since you finished this chapter, is sometimes there's more than one right way to do it, right?
mhm. Yeah, no, that is also true. Um, oh, I was hoping you could like explain how you identify an amine, and then there was another one, it was like an imine or
Yeah,
something.
imine and enamine, and yeah. So this is page like what, like 12 or 13 or
Yeah, it's on page like, what is this? 13.
10 amines as intermediate nucleophiles. This is when we start to see, here's like, this is the really basic um, definition of it right here. So we're turning this carbonyl into an imine versus an enamine, right? So we have this first degree amine and second degree amine, then
Yeah, so
becomes,
I'm
yeah.
not like clear though on like the like defining characteristic of it. Isn't amine or an imine or whatever? Is the defining characteristic of that a C double bond N? And then because that's not present if you go down to the anamine, so then is that one just a C single bond N and
So
a C double
yeah,
bond?
so the important thing to remember is that like there is a double bond associated with the enamine, but because nitrogen already had, it was a second degree amine, unless it became a formally charged molecule, it can only create one bond with carbon, but we still are seeing this double bond, this pi bond characteristic. So we're still holding on to the double bonds that we have, right? They're just in an enamine, they're shifting due to nitrogen not having the space like an imine does. Does that make sense? It doesn't have the electron, what are they called? Electron, geez, domain. Thank you. So this one's like, this is like 1, 2 domains, 3. Oops, I'm sorry. What is, I think it was like 1, 2, 3 domains. This says 1, 2, 3 domains, right? And then this is our lone electron pair. So 1, 2, 3 plus our lone electron, 1, 2, 3 plus our lone electron. And then I know this is like not helping because it's like, because it's so thick. But yeah, so we're still holding on to that pi bond. This pi bond is still here. This pi bond is still here, just like it is in the original. But it just has to do with their like electron domains.
Okay. Yeah, understood. Okay. All right.
So, but if you had like something like this, right, and you had this, oops, I think he's glitching. I'm sorry. So if my notes end up being funny, I'll try to fix it when I see them. So this is supposed to be just a single bond, right? But if you have like this over here, that is not an enamine, right? Because it's not associated. I think the thing maybe to remember is like, is the pi bond still somehow associated with this carbon that was once connected to an oxygen and now connected to the nitrogen? Right? See how like this pi bond here is still associated with that same carbon versus this pi bond here is not. Does that make sense?
Yeah, like the double bond is like, yeah, like they're not all in a row, basically. Like it doesn't have to go like the nitrogen and then the carbon that's double bonded. That's the point you're saying in the purple one, is you have the nitrogen and then the carbon, and that carbon is not the one that has the double bond on it.
Yeah, it didn't. This carbon here did not originally have the double bond. It was this carbon here that originally had the double bond, which is why I'm saying
Yes.
pi bond, because they all have sigma bonds, right? But it's the pi bond that we're like looking at, right? So it's this pi bond, this pi bond, this pi bond, right? It's the second, it's the double of the bond, right? So that's
Yeah.
what I mean. Yes. Is like, is that pi still associated with its original carbon, which are, whoopsies, which are these ones here, right? Those are the original carbons that had those pi bonds.
Okay. Yeah, and then yeah, like can you also just like explain like on page 13, I think as well, I don't know what page are we on right now?
I'm not sure what that one was, but I do, I have 13 as well.
Okay.
So this is formation of enemies.
Yeah, so it's like
Yeah, we're
it
like
says
in this area.
imines are used in synthesis. Oh yeah, right there. Yeah, at the bottom of that page, that last example. Can you just explain?
Yes.
Can you explain like how you know, like I just don't know how you get to know the final product, like after the step that's like, you know, MENH2, like how do you know that the it's gonna form this like structure, like that, like the carbonyl is gonna turn into this like nitrogen with the double bond. Like, can you just explain how you know that?
Well, okay, so I mean, this kind of sums it up a little bit, right? It's a first degree amine because this is what it looks like. N N E H H, right? That's what this yellow looks like, right? And
Right.
so we've already made the decision that it attacks this carbonyl here, right? So we've already made this distinction that we're essentially replacing this O of the carbonyl with this N, right?
Right. But then
But
it has a methyl on it.
yep, this methyl right here, and that methyl is still right here.
Oh, okay. Yeah, okay. I just got confused, I think.
No worries. Yeah, I know. Sometimes when it's like we're using like abbreviations and then we're going to line angle, it's like things can get a little kind of funky, right? So I get
But
it.
then one of the protons, I mean, one of the hydrogens is gonna have to get deprotonated, is that right? Because then wouldn't nitrogen, because nitrogen has, um, oh, okay, never mind. Yes, actually, no, that's right, right? Because
So
the
what
nitrogen,
happens right
yeah.
here? Look at this mechanism right here. This is basically the same thing, right? So what we're doing is we have this here, right? This is our carbonyl. Same as we are up in this area, I think. Yes. Okay, so this carbonyl here is the same as this down here, right? Like we can just extrapolate that from the sizes, right? I mean the structure. So what's happening is this NH, this is still an imine, right? It's an R, this, instead of R, this is methyl, right? But it's still an imine, not to be confused with amine or enamine. And so what's happening is this nitrogen is coming onto the carbon here, right? And so now we have this. Well, now we have our positive, or I'm sorry, negatively formal negative charge because we pushed the electrons from the double bond up onto the oxygen, right? And so then what happens is the order of protonation, deprotonation is ambiguous, right? That's why we don't have a lot of these like mechanisms necessarily like that we know exactly what's going on. We just know that it has to be happening in order for this to happen, right? So we don't know basically, does this get protonated first or does this get deprotonated first? Like we're not really sure, right? But either way, something happens where we end up with this product right here, right? And then once we have that product right here, we reprotonate, not reprotonate, but we protonate from our catalyst, right? So we protonate this to become here, right? O2, right? Sorry, H2O, which is our water, right? And so then that becomes a good leaving group. And so that comes off, and then we have this resonance structure here, right? Where here's the carbon from our original carbonyl. Right? That's that same carbon. Okay. We're just flipped around in the other direction, right? And then so here we are, right? So then these come down here for our little resonance. Oops. Yeah. And then we have our double bond. That's where we get back to this, right? Imine double bond situation. So then we deprotonate this one so that this comes off. And that's what leaves us with this. And there's obviously this H here that we're not. Oh no, not this one. Just kidding. The H here was there, right? And then that's how we end up with this. And that's our O2 as well. Right?
Oh yeah,
I
I like,
the
I
H2O here.
see it. Okay, yeah, yeah, like now that you like broke it down, like I see. Yeah. I don't know. No, I
I
see
know it
it
can
now.
sometimes be hard, like, because when you like are just given like the before and after and like the reagent or yeah, the reagent, and you're just like, oh, okay, I'm just supposed to know that. But that's really what's going on, right? You're just, this is attacking your central carbon, then you're doing some form of protonation, deprotonation. We've got both protonation and deprotonation, then we have protonation, then we have deprotonation, and then we end up with this amine, right? So this is where we start getting into that, like, add this, take this away, do this, do that, right? So that's where some of that stuff is going on.
Okay. You see what else? Mm, um, let's see. Oh, the other one was on page 14. I think this is a really similar case to the one you just explained, but I just want to make sure. So it's the
We're
one
like
that's
in
like,
this area.
oh yeah, that one that you have on the screen. On the top.
Yep.
Yeah. So, okay, so yeah, so how do you know that like can you just explain how you know to get that enamine in the middle?
Okay, so again, what's happening is you're having this. Let me just make sure this is what's happening before I explain anything. Because you're adding this. So what's happening is you're coming. Because there are no protons on the nitrogen to deprotonate. Your reaction sequence above is the Gilbert-Stork enamine synthesis. It will be one of our final carbon formations. Yeah, so I believe it's happening the exact same way as far as like where you're doing this do I have it in here also? Oh yeah, I do. Like yeah, so it's basically this same exact scenario as far as like what's happening, right? Is like you're having this time we have a second degree amine, right? You can see that, correct? We have 1, 2, right? Second degree amine.
Yeah.
So that means that we're going to an enamine, remember, means that we are kind of like replacing, right? I'm using this term a little bit loosely, right? But we're kind of replacing the oxygen on the carbonyl, this one right here. And because we have a second degree amine, this pi bond can't sit here, so it will move to this one, right? Essentially, right? Like I'm kind of extrapolating through resonance, right? This up here shows you, right? It's through resonance that ends up happening.
But I don't understand how that moves because isn't carbon an sp3?
Wait, sorry, say that again. You broke out.
So in the first structure where you drew the purple arrow to show the double bond moving, isn't that carbon on the right? Like if you
It is.
number
It is. So we're making that double bond by pushing the electrons up onto the nitrogen because it has a positive charge, and we're taking this hydrogen and it's essentially leaving, right? The hydrogen is leaving so that the the electrons from that hydrogen then create this. So this now becomes an sp2 hybridized, right? That's this right here, but it's in the opposite direction, right? So this carbon, let me draw it in a different color. This carbon, because the hydrogen left, right, bye, and these electrons moved into the
see it
pi bond.
now.
Yeah,
Yeah, I see.
yeah. So yes, this was initially, right? But remember, we have these hydrogens. And so in this case, what ended up happening was this hydrogen, it was taken off by somebody, right? Whatever it was, right? It was, relieved of its position, and the electrons were then used to form the pi bond, because the electrons had, let's imagine this was the N with its pentane ring, right? So what ended up happening was these got pushed up this way because this was a positive charge. And it said, I didn't want that. I'd rather have my lone pair of electrons. So the lone pair of electrons got drawn upward. And when that happened, this was also able to come in and create that pi bond, which formed this, right? And that's what we see over here. We see this with its electrons, and there's the pi bond.
Yeah, okay. Yeah, I
So it's not like, it's not like, oh, this, without anything else going on, but just straight up this pi bond here is just now migrating over here, despite the fact that we have hydrogens. Like, yes, you're right, that it was sp3 hybridized, but we had to like do some rearrangement of things to make that happen. So
yeah, I see. Okay. I'm trying to see what else there was. I don't know. I feel like okay, on that same question though,
the same area here.
like no, the exact same one we're just on though.
Oh,
But then
okay.
can you explain the next step with the phenol reagent?
Yeah.
So like how do you,
So-
I just don't understand, like by looking at that reagent, how you know you're gonna regenerate the ketone?
Yeah, so with this, what ends up happening is let's see, let me here CH2, right? And this is, and remember, this is 1 and 2, so this doesn't happen at the same time that this happens, right? So just to be clear, so remember that bromine's a good leaving group. Excuse me, bromine's a good leaving group. And so what's going to happen is these pi bonds are going to want to react with this here. I don't know for sure. This is probably an SN2 reaction, right? Where, well, maybe not because it's a first degree, but either way, it's probably, it might be. Anyway, these pi bonds are going to then react with this CH2, right? This one right here, right? That's what this is. The CH2 here. The bromine is going to leave. It's going to leave us with this is all the same, right? Those are all the same. No. Let me back up. Those two are the same. There we go. This C, and this are the same. There we go. That's why you should count your carbons. Yeah, so anyway, and so then what ends up happening is then we have basically like a kind of like a regeneration where this will end up coming off. Well, because I don't have it written out really, do I? So this ends up coming, let me see. So these get pushed up. Wait, which electrons? Because these end up becoming. Oh, these electrons get pushed down. Okay, that's why. Because I'm like, where do these other electrons come from? These electrons get pushed down here because this becomes like a positive, right? So then this electron gets pushed down here, so making that a double bond there, because now we have this new bond between here, which is this. And so then what we end up having is that same N, but it's positively charged. And a double bond, and then we have our okay, and then now we have this positively charged nitrogen there. Well, when we do our acid workup step, what's going to end up happening is that same thing, right? So then now we have, that's why this is a separate step, right? Because in order to get to this is all part of one, right? This is what we end up with when we add this to one, right? So we have this good leaving group. We have this connection that's happening between this pi bond here and our CCH2 here. And then what happens in step number 2 is because we have this positively charged, this anion, formal positive charge on our nitrogen, we add in our H3Os, right? We add in our H3Os. And then so this gets protonated, and that pops out there, this gets protonated, and then we end up having this space here where we're kind of back to that, right? So we have oh yeah, that's right. You don't, this isn't like, we don't have to know all these mechanisms, by the way, not that I know of, but and so then we have this positive charge here. No, not a positive charge here, because we have, oh, we have this double bond here. How does this end up? The oxygen from our acid workup step ends up coming on here. I don't exactly know which exactly, but it ends up attacking here. It must be because these pi electrons leave somewhere. Maybe they come back up here. No, they don't.
Like,
Yeah, they do.
isn't it like, I don't know, like from looking at it, I feel like the only way you can get an oxygen on there obviously is from the water or the hydronium. But
Yes.
but so like that, does that mean that that whole like the
The
like
second degree
ring,
amine basically is like it comes on.
but like that entire ring with the nitrogen on top, that has
Yes.
to be a leaving group, right?
Yes. Yes. Exactly.
Okay, so just like, so
You're
basically like
basically regenerating this. That's basically what's happening. You're kind of regenerating that to like have it leave.
yeah.
But you
Okay,
can't
okay.
just add this on because this is not going to react with this, right? So that's why we put it on here first and then put this on so that we can then have that, we can put this piece here on, right? Because we don't really have any way to like make this happen, right? So we can't just like,
Yes.
so that's why.
I see. Yeah, no, I'm getting the gist now. Like I wasn't seeing it before, but I see it now. Okay.
Yeah, it is hard when you have like all these like protonation and deprotonation steps because it's like how do you follow it along? And this one I don't exactly know what happens. This is obviously this is a neutral molecule, so then when you have this, if this isn't a double bond, anyway, we don't have to figure this out. But this is 1, 2, 3, 4. Maybe it's because I'm missing. It's not yeah, it's positive. So if it's 4 and normally it's 5, yeah, 5 minus 4. Yeah. So that's right. But then it has to get so either anyway, it would get protonated and deprotonated anyway. I don't want to waste your time trying to figure out the mechanism exactly, but I'll figure it out on my own time. but yes, that's generally speaking, that's what's gonna happen. But I don't know as you need to necessarily know the whole yeah, you're gonna like learn more about this later in the course it's saying here, but like how that stuff is made. But I think some of this stuff is they're basically like trying to like introduce these concepts to you and have you see it, but you don't necessarily have to do all the mechanisms and curved arrow pushings. So for this one, I don't think you have to know too much. But yeah, I mean that's essentially what it's doing. You're basically just like regenerating this in the end. So then this would like, be like plus NH, right?
Okay.
And there's more mechanisms and stuff that you don't necessarily have to know, but just know like what comes out of it on the other side, you know?
Mm-hmm. Yeah, and then also, would it be possible to go over some questions from the last test?
Yeah. What ones?
Like I have like the specific numbers that
Yeah.
like I guess starting at 5
What was the last
because
test? Number 4? Was that the last exam? Was that
yeah.
4? Yeah. Oops. Um, okay. All right. Yeah. What? Go ahead. What question number? Can you hear me?
Yeah.
Okay. What question number?
Yeah, the first one was 5.
Oh, okay. Maybe I couldn't hear you. Sorry.
It was literally just a thing about the like electrons and like Huckel and stuff, which I thought I knew
Assuming the
for
following
sure.
structure is flat and planar, indicate whether it's aromatic, anti-aromatic, or non-aromatic, according to the Huckel rule. Is that what you're
Because you
talking
know
about?
how, yeah, because like, you know how we had discussed the thing about SP3? I just wanted to make sure that from that example, like,
What
because
is
it
your
had
what does your molecule look like? I don't know
um,
which class you're in. There's 2 different chem classes, and so I don't know if you guys' exams look the same.
oh, it's a 1, 2, 3, 4, 5, 7. It's a heptane ring, and there's 3 double bonds. Like it looks aromatic, but it's heptane, and then on the carbon that doesn't have a double bond, there's a positive charge.
Number 5. Oh, I definitely don't, unless it's the same one. You know what the last 4 digits of the class numbers? Oh, are you in the 40011 or whatever? Your class number. It's okay if you don't remember.
I'd have to look.
Don't worry about it.
Let's see. 40011.
Okay, yep, got it. Okay. So 1, 2, 3. I hate drawing. 1, 2, 3, 4, 5, 6, 7. Jeez Louise. And then positive here, and then this, and this, correct?
Yeah, so I just want to make sure with this one. So like, do you just count the double bonds? Because the positive charge means like it is not SP3.
Yeah, so right, yeah. Well, because this is a line angle structure, I don't know if you could, well, for sure, it doesn't necessarily mean that it's not, because there could be one hydrogen here and it's missing a hydrogen, right? And so that's why it's positively charged. That could be the case. But when it's asking for the Huckel rule, that's a 4n plus 2. So regardless of when you're counting, there's you know, 3 things that you have to like think about, like, is it planar, is it conjugated, and is it whatever the other, I think planar, conjugated, and what's the other thing, planar, conjugated, and why can't I think of it?
Again, just like how many electrons there are.
Oh,
Right.
cyclic. Jeez Louise. Cyclical. Like, what is it? But yeah, I mean, it's assumed obviously this is cyclical, like, right? But yeah, so you would count how many electrons there are. So there's 6. So it's in a 4, there's 6 electrons that are participating in this reaction, right? So you have, this is a Huckel, right? So according to the Huckel rule, which means that it has to be 4n plus 2, right? Aromatic 4n plus 2. Indicate whether they are aromatic, anti-aromatic, or non-aromatic. Yeah, so
So then that's what I had done. I said
it's
there was,
conjugated.
yeah,
go ahead. It's
yeah,
conjugated, it's cyclical, it's planar.
yeah. And then there were 6 electrons. So I just said that, yeah, if you solve for n, it's an integer. So then that means it's like Huckel, right?
Yeah, it would mean aromatic. Is that what you're trying to ask, or no?
Yeah. Yeah, so that's what I put. I just wanted to make sure because I just wanted to make sure, like, because I don't know, like on the test there were only 2 of these, and like they both kind of seemed to be that, and I was like, does that mean it's wrong?
I get what you're saying. Like, what you mean? Like, you're saying that there was like other, there was other like, molecules that you were asked the same question about, or?
Yeah, there were 2 of these examples, so I thought it would be weird if they were both aromatic.
I wouldn't, don't be like, oh, well, I've already had C a couple times, so it's probably not C again. I wouldn't worry about that, like I would just go with what you think is correct according to the information that you've learned, right? So
Yeah, I know, it's just you
this is
get
a
that, like,
cyclical
you also get
conjugated.
that, like, feeling,
Yeah,
like,
the second thoughts and the doubt. I get it. But yeah, no,
so you
we're
would
given
say
that it's
it's
planar.
aromatic.
I would say that's aromatic, yeah, because it's planar.
Okay.
We're given that it's planar. It's obviously cyclical. It is a conjugated system because conjugated system, yes, you can't have an sp3, right? So you have to have all sp2. So I would assume that that's I can't say for sure, but I would assume that obviously like that plus sign means that typically like conjugated means that like if the plus sign is there, that means that electrons can move into that area, which means that it can't be, like if it had a hydrogen there. Either way, the positive charge, that means that electrons can move there, right? So even if it did have a hydrogen there, it could still, take on that pi bond pi character. So yes, conjugated for sure, because every other is a double bond, or you have some sort of resonance capability with the positive formal charge. And then it's asking according to the Huckel rule, right? So with Huckel rule, it has to be 4n plus 2 to be aromatic. So I would say aromatic, yes.
Okay. And then can you also go over 10?
Yes. 10. What is or are the reagents for the following reactions? Or
No,
reaction?
mine was like,
Oh.
do we have a different order?
You
Mine
might.
was like,
Again, I have that kind of the like, but yes, tell me. What does yours look
it
like?
was just like, it was like the hexane ring, and then there was 2 double bonds with like there's a double bond and then like just a space and then another double bond. And then
What's the question ask?
it's asking for the final product, and it has like KMnO4 OH and Boyle with hydronium.
Yes, let me see. And it's a what? It's a hexane ring, and then what? Anything else?
Yeah, with 2 double bonds, and then there's there's like 1, 2, 3, 4. There's stuff coming off of it. There's like some substituent groups coming off.
Let me see. Let me see. Okay. Okay. What does okay, so you're saying that it's a hexane ring. Right?
Yeah.
And then what?
And then draw 2 double bonds, but with a space in between them.
So one here and one space or 2 space?
1.
So one here?
Yeah. And then on the first, basically the most northern like point.
Yeah. So 1, 2, 3, 4, 5, 6. Okay.
Yeah, so now go to the most northern point and you draw
So on carbon
like,
1?
yes, carbon 1. Draw, it's like 1, 2, 3. What's 3? It's not an ethane, it's a propane.
Yeah.
Right, or a propyl.
Yeah.
Light
so 1,
thing.
2, 3.
And then on that again most northern, like go to carbon number 1 and go up 1 as though it was a methyl, then there's another methyl coming off of it.
So like this?
Yeah, that's it. And then the reagent was the KMNO4 with hydroxide boiling and then hydronium.
Oh, okay. So, all right, and then I'm just gonna redraw this a little bit better. Okay. 1, 2, 3, 4, 6. And then this, and then you have the propane plus another methyl, and then you're saying that it is KMNO4 boiling. Oh, and then what was the other thing? Oops. Did you say acid work up stuff? This?
Yeah, that's right.
Okay, and then so what's the question?
Yeah, so it's just asking for the final product.
Okay. So going back to let's see. Order this up here. Okay. So going back to this one. Yeah. Okay. So when we have this reagent, basically what you're doing is you are oxidizing, right?
Right.
So when you are doing, let me bring up, pull this, make sure to do this on both sides. So it's an oxidation reaction, and you end up with like an alcohol. Where is it? It's in the benzenes chapter. Yeah. Oh, right here. Oh, right. So this has to do with like your electron donating groups, your electron donating groups or withdrawing groups or whatever, right? So you are with any alkyl group, a benzylic alkyl hydrogen is oxidized. That's what happens in this one. That's right. So benzylic hydrogen is oxidized to create, oh yeah, that's right. You're making like either you're making what's it called? Carboxylic acid. That's what you're making with this. So that's what you end up with.
So yeah,
yeah.
that's what I put, but I like wasn't 100% confident because I kind of forgot the like mechanism.
Yeah, I think that this is one of the mechanisms that you don't actually know. Like, I don't think that you have to like know too much. Like, let me see, because I don't really remember really good mechanisms for this one. Um, Yeah, the mechanism, it says mechanism isn't completely known except for the first step. It's a radical. It's a benzylic radical step. So that's what it is. Because your KMNO4 is, you're basically starting off with like, anyway, we're not going to draw out the mechanism because we don't know it. But the short story is you are adding a carboxylic acid, or you're like, you get a carboxylic acid. So, this is like the beginning steps of it, right? And then so you're taking one of the benzylic hydrogens, which would be, this is a benzylic hydrogen here, right? Yes, be that hydrogen there. And then you would, you're turning that into your, so this is what ends up becoming where your carboxylic acid is. That's like a kind of essentially, as long as you remember, A, it's going to be carboxylic acid, and B, it's going to be at the location of like a benzylic hydrogen, then you should be good.
Okay. Okay.
I think those are the two main takeaways from that.
Okay. And then also, it was my number 12. It was asking, it had this like pretty complicated structure with 2 rings, the nitrogen connecting them. I don't know if you can like scroll through and try to see, because like to like describe this would be a little bit challenging. I mean, it wouldn't be too bad, but okay, yeah, you got it.
Yeah.
Okay.
It's a diphenyl.
Okay.
Okay. Yeah. And your reagent is this one. Whoops. HCl.
Yep.
ACl, AlCl3 or whatever.
Yep.
CO, oops, not cobalt. HCl, AlCl3. Right. Okay. So yeah, so this is are these done? COHCl, AlCl3. Oh yeah. Okay. So this is you're basically adding an aldehyde, I guess, would be like the best way to think about it, I suppose. Right, because any of those mechanisms you're just adding like an aldehyde. So which I guess, yeah, that's all your options too. They're just only adding aldehyde. So I guess what you're wanting to know is, how do you know where to put it?
So yeah, so let me just look at what I written. I said, yeah, so one thing that was getting me confused was I thought I recalled from last gap notes that it said when you have a halide, like bromine is, then it's either it's O and P,
Yeah,
right?
it is still a withdrawing group, but it will place molecules on the ortho-para position rather than the meta position. So it's considered like a, I don't know if like neutral is the right word for it, but like it's not neutral, but it's like it is like halides are kind of like those like exceptions to the rule where like they
Yeah,
are technically a withdrawing group, but they'll put things on ortho-para positions like a donating group. So
right. And then yes, then that's what I thought I remembered. And then on the other side where I said that the methyl group was a donating group.
yeah.
So I said then that will also do O and P. But then 2 out of the 4 choices were like, so I eliminated the meta positions right away, but then 2 out of the 4 choices had a position one right next to bromine, which would be the ortho, and then one right next to methyl, which would also be ortho. And to distinguish between the two of them, I use the argument of like steric effects. Like I said that there would be more steric effects next to bromine than there would methyl, so then it would add next to the methyl. But I didn't know if that was right.
So okay, so let's think about this as 1 and 2, because each of these phenols they have both of these things happening, right? But like if you were looking at when you have this position, it's it is kind of considered like a donating group. I mean, a withdrawing group in a sense still. So it wouldn't necessarily be on that ring, right? As opposed to when you have this green ring, you have like donating groups. So you're gonna listen to your donating groups before you're gonna listen to a withdrawing group, right? So
Okay.
in this case, so bromine, even though a halogen is kind of an exception to the rule because they're ortho-para directing, it's still considered a withdrawing group. And so if you have a withdrawing group on one and a donating group on the other, you're not going to do the one with the withdrawing group, right? Regardless of it. So then we have to look at this ring here. Well, this ring as a whole has these 2 groups on them. And so between these 2 groups, there's a methyl and there's an amine, right?
Right.
So between the 2 of them, the amine is going to have the greater donating ability than the methyl. So you would, on this molecule, on this side of the molecule, I should say, on this phenyl, you would listen to this donating group, the amine, over the methyl. So then you would make your
Okay.
decisions on ortho-para based on that donating group. And this para position is obviously already taken due to the methyl. So it would have to go either here or here.
Okay. Yeah. So I have a question though on that. So
Yes.
because the reason why I didn't look at the N thing is because like I didn't know which one, like which you could say it belonged to, the ring on the
Both.
right or the ring on the left. So like I
Both.
just
Belongs to
yeah.
both. That's why I drew the circles, the green circle and the red circle, because it technically belongs to both. But so since this is the common denominator, then we have to look at these other substituents. So between these 2 substituents, this is a withdrawing group and this is a donating group. So we for sure are not going to do this ring because it has a withdrawing group on it, and we'll always listen to a donating group over the withdrawing group. So now that we
Yeah.
know we're going to use the left side ring, now we have to look at the ring as a whole.
Okay, yeah, I see now. Okay, okay. All right.
Yeah. You have to find the differences when you have these two, this diphenyl situation, you have to find the differences between the diphenyls, between the two phenols, to decide which one you're going to look at. And then once you decide that, then you have to go back and kind of look at it as a whole, because that nitrogen is still obviously connected to it. But that was just the common denominator between the two of them. So we couldn't use that to make our initial determination, right?
Yeah, no, I see. Okay. And then could you just briefly also go over 14? It had like the ring and then it had like methyl on one side and OCH3 on the other.
Methyl on one side and OCH3. Oh, okay. I'm just gonna erase this stuff. Alrighty, so we had there. Okay, and then so what's the question? Just like
Like-
what?
Oh, like
Yeah.
what was it asking? It had the like it asked for the final product
yes,
given
yes.
that reagent.
Let me see. So Cl is going to be our group that comes off, right? So this is a Friedel-Crafts acylation. So you're basically just determining where this will go, and what you're going to be adding to is right here, right? So basically, you're just deciding which carbon, right? Which carbon here this is going to go on. So again, it just comes back to like donating versus withdrawing groups. They're both donating groups, right? But which one's the stronger donating group?
The OCH3.
Right. So it's got to go in one of those three places. Can't go here. Methyl's already there. So this has to go either here or here, right? And then we would get or, right? Not both, but or. Whoops. Not that. One or the other, not both. Just to be clear. Right. So just depending on what your answer choices were.
Okay. Okay, so what is the function of the aluminum trichloride thing?
Yeah, it's to because this is coming off, right? So it'll pick this up. It's like a catalyst stabilization, right? Like you're
Oh,
creating that kind of,
okay.
you know.
I see. So it's like doing a substitution with the first one.
Yeah, essentially.
Oh, okay. Okay, yeah, I see. Okay. Yeah, I think that was it.
Cool. Yeah. Yeah, no, that the OChem 2 is a doozy. I'm not gonna lie. It's a lot. There's a lot of stuff going on. So it's it's just synthesis after synthesis after synthesis of learning like all these different reagents and reactions, and it's a little intense. I'm not gonna lie.
Yeah.
I did not love OChem 2. I did all right. I mean I did well in it, don't get me wrong, but it was not easy. As I say, I fought for my A in OChem 2. I did not feel that way in OChem 1. So